A very good day to Inchi Aminuddin. Today, I, Wanissa, and my groupmate Debra will be presenting our findings for a project titled An Econometrics Analysis, Bitcoin versus Other Cryptocurrencies. Now, let's get right into it. Now, let's talk about the main topics surrounding our project with the main question, what is cryptocurrency? Now, a cryptocurrency, usually referred to as crypto, is a form of electronic money that may be used for transactions across computer networks. It is decentralized since it is not supported or managed by a single entity. In addition, it's important to understand that cryptocurrency eliminates the need for a traditional middleman, such as banks. Despite what the name would actually imply or suggest, it's crucial to understand that cryptocurrencies aren't thought of as traditional currencies, such as ringgit Malaysia, US dollars, and etc. Each cryptocurrency functions utilizing distributed ledger technology, which means it frequently involves a blockchain that, when utilized with decentralized control, it presents as a public database of financial transactions. Now, cryptocurrency has acquired its name because transactions are encrypted and validated. This means that complex code is required for the storage, transport, and recording of Bitcoin data to public ledgers. So this is the actual purpose of encryption, which is to provide security and protection to its fellow users. The cryptocurrencies we'll be analyzing are Bitcoin, Litecoin, Ethereum Classics, Bitcoin Cash, and Ethereum. We have decided to make Bitcoin our Y, also known as the dependent variable, whereas the rest of the cryptocurrencies observed are our independent variables, also known as X1, X2, X3, and X4. Now, the reason why Bitcoin was made our dependent variable is because it is the most well-known and frequently utilized cryptocurrency among cryptocurrency traders. Additionally, when analyzing cryptocurrencies, Bitcoin has consistently come up most frequently, particularly during the height of the COVID-19 pandemic. So these are the reason why we choose Bitcoin as our dependent variable, just to ease up our analyzation process. Now let's move on to descriptive data analysis. Now we actually chose line graph as our plot of choice. Line graphs are used to track changes over periods of time. So this means when smaller changes exist, line graphs are better to use than bar graphs or any kind of up graphs actually. Line graphs can also be used to compare changes over the same period of time, but for more than one group. So the line graph was used to represent its respective variables, which are y, x1 to x4. And as you can see, it is to ease up the analyzation process to easily identify its fluctuations and trends. And according to these graphs, there are many fluctuations to take note from. Therefore, this actually helps us identify breakpoint dates for our child test and also to ease up the analyzation process, as we all know that when analyzing cryptocurrencies, line graph is the best choice. Now let's move on to Model A. We've used the ordinary least square method to analyze our regression model. So what really is the ordinary least square method? In the linear regression model, with a fixed level 1 effects and a set of explanatory variables, the ordinary least squares OLS method uses the principle of least squares to select the unknown parameters by minimizing the sum of the squares of the differences between the observed dependent variables values in the input and the result of function in the independent variable. Now let's take a look at model A. The coefficient between Y and C, the instance of model A, is valued at 2,292.511, meaning that if C increases by €1, Y, which is Bitcoin, would increase by 2,292.511, and so on for the other variables. This model has an R-squared value of 0.939947. This shows that approximately 93.9% of the variation in the output can be accounted for by the independent variables. Now, the fact that the R-squared number is close to or approaching 1 or 100% indicates that the regression model matches our observation well, which also signifies that the regression model fits the data according to this model. In addition, this model's standard error is roughly estimated to be at 3,617.159. This shows that how far the observed value deviates on average from the regression line. And last but not least, the model's overall p-value is set at 0.0000, indicating that the independent factors have a substantial impact on the dependent variable, also known as y. As we move on to model B, the log model, log y, increases by 4.133096, which means when C increases by €1. The coefficient values from the regular model without log are noticeably lower, as evidenced by the findings. Nonetheless, the model's R-squared value, which is valued at 0.970897, indicates that the independent variables account for roughly 97.1% of the variation in output, leading to superior results. Moreover, the log model's standard error of regression is estimated to be at 0.1223667. The p-value model is also valued at 0.0000 throughout the entire model, with the exception of variable log x1. The child test is a test of whether the true coefficients in two linear regressions on different data sets are actually equal. The error terms in the sub-period regressions are normally distributed and have the same variance, also known as homoscedastic. Moreover, the error terms known as mu1t and mu2t have separate distributions. So the breakpoint date for this sample, as indicated in figure 5.0 child test, is on 12th of March 2020, which indicates that the COVID-19 pandemic produced structural change in our data. The epidemic was at its worst in the first few months of 2020 and also generated a financial crisis that disturbed the Bitcoin market, making it erratic and unpredictable. As a result, this OLS model that uses time series data demonstrates that there has been a structural change between the regressors X1, X2, X3, X4, and the regressant Y. For our model, the COVID-19 pre-transition pandemics to the pandemic phase at in the month of March 2019 was the primary cause of the structural change. Now let's move on to multicollinearity variance inflation factors. A variance inflation factor, VIF, is a measure of the amount of multicollinearity in regression analysis. Multicollinearity exists when there's a correlation between multiple independent variables in a multiple regression model. This can adversely affect the regression results. Thus, the variance inflation factor can estimate how much the variance of a regression coefficient is inflated due to multicollinearity. One of the ways to detect multicollinearity is through VIF values. The independent variables x1, x2, x3, and x4 in this model exhibit a strong example of multicollinearity, especially for the variable x1 with a value of 12.38814 according to the variance inflation factor's value. Now, multicollinearity would theoretically always exist in a model. Hence, it's critical to find its severity or to lessen it in order to get more accurate results or predictions for the model. When any variable or more than one variable measures a VIF value of greater than 10, the variable or model is said to have a severe case of multicollinearity. After several removals of different variables to lessen the severity of multicollinearity, as you can see, the removal of X3 provides a better outlook and lessens the seriousness of multicollinearity for model A. As compared to the previous VIF values, the removal of variable X3 has given a better outlook, with a value recorded at 2.115784 for X1 and 3.659053 X2 and 4.208375 for X4. All the variables have recorded a VIF value of below 10 and closer to 1, which has lessened the case of multicollinearity significantly in Model A. Now, let's take a look at Model B, our log model. Model B, however, has different results as compared to Model A according to its VIF values. The VIF value for Model B recorded two variables, which are log x1 and log x4, with a value of 8.572159 and 9.315684 respectively. So these values are approaching 10 and shows the severity of a case of multicollinearity for Model B as well. So the removal of X4 has shown a result of low case of multicollinearity despite its VIF value being more than 1, as long as the values are below 10. So this shows that the removal of X4 is the best for model B and has the lowest case of multicollinearity with the removal of X4. Now let's move on to multicollinearity detection through auxiliary regression for model A. When the R-squared value is higher than 0.80, it means that the case of multicollinearity is serious. Non-dependent variables such as x1, x3, and x4 records R-squared values higher than 0.80, which means that a severe case of multicollinearity actually exists in model A. However, x2 are the only dependent variables with a value below 0.80. However, in the case of the log model, dependent variables log x1, log x2, and log x4 shows an R-squared value of higher than 0.80, which means a severe case of multicollinearity. However, log x3 is just right below the 0.80 limit for a severe case of multicollinearity, which is set at 0.784629. So this is basically how we detect multicollinearity using VIF values and auxiliary regression. Now these two are great methods, but there are many other methods to overcome multicollinearity as there are adverse effects or impacts that multicollinearity bring to a model. So it's important that we try to lessen the severity of multicollinearity.
Now, I'll be explaining about heteroscedasticity. The conditional variance y rises when x rises due to a phenomenon known as heteroscedasticity. Heteroscedasticity is present because the variances of y are not equal or what we known as non-constant. In correct data collecting techniques, the presence of outliers, a correctly specified regression model because significant variables are being left out of the model, skewness in the distribution of the regressors in a model, inaccurate data transformation, and functional form are a few causes of heteroscedasticity. When heteroscedasticity is present, the variance value is not at its minimum and the ordinary least square OLS estimator is not blue, also known as best linear unbiased estimator. The estimate is nevertheless still linear and equal. Therefore, it is crucial to convert the model to generalized least squares, also known as GLS, which involves changing the original variables so that they meet the requirements of the classical model before applying it to the OLS estimator. In its simplest form, GLS is OLS with modified variables that follow the orthodox least squares presumptions. Since these estimates are now blue and have a lower variance than OLS estimators, they are known as GLS estimators. Using the white test is one technique for spotting heteroscedasticity. By regressing the model and collecting the residuals, NR² can be calculated by performing the auxiliary regression and getting the value of R². If NR² is more than chi² value, we reject the hypothesis that there is no presence of heteroscedasticity. Therefore, heteroscedasticity is evident as a result. The OBS star R² value NR² is 724.3769 and prop F is 0.0000 from our sample from model A. The NR² value, which is 724.3769, is more than our chi² value, which is 13.2767. Hence, we reject H null, which is our null hypothesis. As a result, our model A contains heteroscedasticity. The p-value, which is 0.0000, can also be used to test the presence for white heteroscedasticity as well. When p-value is 0.0000, it is less than a significance level of 0.01. As a result, we will achieve the same outcome and reject HO. Hence, heteroscedasticity is present in our model. Next, for our model B, our OBS star R² value, which is an R² value, is 479.2842, and prop F is 0.0000. From our sample, we reject H null, which is null hypothesis, because NR² equals to 479.2842, which is greater than our chi value of 13.2767. As a result, our model B exhibits heteroscedasticity. At a significance level of 0.01, which is more than our p-value of 0.0000, we reject HO, as it is customary. Our model demonstrates heteroscedasticity as a result. Autocorrelation occurs when error terms are correlated. The occurrence of the business cycle, the excluded variable specification bias, the incorrect functional form, the cobweb phenomenon, data manipulation, and finally, presence of data transformation are examples that contribute to the presence of autocorrelation. The OLS estimate is not blue in the presence of autocorrelation because it does not have minimal variance, which renders the model effective. Hence, there is a chance of overestimating R-square value. The conventional T and F tests of the significance are therefore no longer valid, and if they are still applied, they are likely to yield inaccurate results regarding the statistical findings of the estimated regression coefficients. The Durbin-Watson t-test can be used to see if the model has autocorrelation if the assumptions are met. The regression model's intercept term and the fixed or non-stochastic explanatory variables x in repeated sampling are among the assumptions. Our Durbin-Watson value for model A is 0.557461, while for model B is 0.563129. These values demonstrate that we reject null hypothesis because there is no positive autocorrelation. This is because our d-value is in between 0 and 1.633. Therefore, there is positive autocorrelation in both models. Next, by using Bush-Gottfried test, also known as the LM test. The method involves using OLS to estimate the equation as pasted to obtain the residuals, regressing residuals on the original equation and get the R-squared value. If n minus p R-squared value is greater than the chi-square value, then reject H null. As a result, there is autocorrelation. The BGTS is restricted in that the lag strength or p-value cannot be known in advance. As a consequence, the lag strength can occasionally be selected using the Akai-K and Swatch information criteria. For model A, the NR-square value is 801.9499. N minus p R-square value is 684.589392, which is more than the chi-square value of 34.8053. Therefore, we reject null hypothesis. Hence, there is presence of autocorrelation in our model A. When nr square equals to 801.9499, which is more than chi-square value of 34.8053, we reject H null too. Accordingly, we will have the same result and there is presence of autocorrelation in our model A. For model B, the nr-square value is 729.3337. N minus p R-square value equals to 692.1812688, which is more than our chi-square value of 9.21034. Hence, we reject null hypothesis. As a result, our model B contains autocorrelation. At nr-square equals to 729.337, which is more than our chi-square value, we reject H null. Therefore, we can arrive at the same conclusion that model B contains autocorrelation too. Newey West is an alternative method for correcting OLS standard errors. The corrected standard errors are also called as HAC standard errors, heteroscedasticity and autocorrelation consistency, or Newey West standard errors for short. Additionally, this method is generally used for tart samples. This procedure not only corrects the standard error case of autocorrelation, but also for heteroscedasticity. For both models A and B, the OLS output shows that the presence of heteroscedasticity by using the white test and autocorrelation by using W. Watson's test at the 1% significance level. Apart from that, both models have the same standard errors and their R-square value, F statistic, DW statistics, and white test are the same for the OLS and OLS plus Newey West methods for regular models. Nevertheless, the generated standard error HAC has a larger value than the standard error of OLS, thus producing a t-statistics HAC with a smaller value. This indicates that the OLS method underestimated the actual standard error values. The generalized least square GLS method is a transformation of the ordinary least square OLS method. This is a corrective method in which the model uses GLS method as the recovery step from autocorrelation cases. The GLS method converts x1 to x1 star, x2 to x2 star, x3 to x3 star, x4 to x4 star, and y to y star. From the output, we can see that the Durbin-Watson value has increased from 0.557461 to 1.921722. After conversion from the GLS estimated model A, we can conclude that model B cannot be converted because the variables have negative values. Therefore, referring to the Durbin-Watson table, neither H now nor H1 are rejected at a significance level of 0.01. That is, there is no positive or negative autocorrelation as the Durbin-Watson values are in range, which is 1.921722 is in between 1.715 and 2.285. According to results, multicollinearity is present in the model due to many factors. However, there are ways to overcome the impact of multicollinearity on predictions and results by reducing the severity of multicollinearity as long as it is less than 10, as it is in theory. After multicollinearity, the data showed that heteroscedasticity was present when the variances were not constant, using the heteroscedasticity white test. That is by calculating the NR square value. In addition to that, Durbin-Watson and the Bush-Godfrey test were used to test for the presence of autocorrelation, in which the error terms are correlated. The Bush-Godfrey test was used by calculating n minus p r square value, and Durbin-Watson was used by referring to the Durbin-Watson table. As a corrective method, we use the GLS correction transformation method on the Durbin-Watson value as a discovery step for our autocorrelation case. Lastly, the Newey-West method alternatively corrects OLS standard errors to overcome heteroscedasticity and autocorrelation, especially for large samples without using the GLS method. Thank you for listening to our presentation.